Yeah, feel free to help yourself. Oh, someone already picked up everything. There's only this thing left. You can pick up the signature sheet. Okay, I still have a few more of these handouts. If anyone wants, please help yourself. I think section 8 is out already. Yeah. Okay, you should be recording. All right, let's start, everyone. Let me bring up the mask. I hope the drilling up there stopped. I called the department and I hope they stopped that. Okay, I have posted here the extra lecture for those of you who need. As I mentioned, highly recommended, and it's really on a need base. Let's put it that way. My plan for today, and has always been the plan, but I'd like to explicitly make it as follows. Let me, before I go into the details, I'd like to remind you that do pick up the signature sheet, put on the date, but sign only after 2:40, so indicating that you did indeed stay for the whole session, and fill out the midterm feedback form if you could. Actually, there are now 23 respondents. Okay, and I have updated the list of the active learning credits, so you can check from meeting 28 to meeting 32. Okay. I'd like to go to something that you are very interested to hear, would be the report 4 problems. Okay, I want to coach the class. In addition to the solution guide that I already posted, I'd like to say a few words. Still, even though it listed as 1, 2, 3, 4, 5, 6 problems, but within each problem I cut down the amount of work. I removed 4.3. So if you compare to the work of last semester, the student did a lot of work. Okay. But I'd like to mention the following. Okay, so this is the big picture of not just today, but if we don't finish, we move on. I move the parts that I couldn't finish to the subsequent lecture. But if you look at the big picture, okay, I'd like to focus on section 8C. I call that the street fighting method. Okay, I don't remember whether I posted the links to the street fighting mathematics. Let me look up here. Go to the portal. I would post if I did not post in part A, and if you look at the list of topics, maybe I might as well do it now, as I'm on the list of topics. The list of topics has everything. Okay, and street fighting mathematics is the actual course at MIT with that name, street fighting mathematics. And let me post at the top of our lecture summary today. So in case someone had wondered what it means by street fighting mathematics, you have it here. Okay, so you can go into this MIT site. It's MIT X. So that's the book. Massive open online courses that anyone can sign up and learn. And there's the book, Street Fighting Mathematics, the Art of Educated Guessing and Opportunistic Problem Solving. Okay, and the MOOC at MIT X. This is the course title and course number. And just to take an excerpt, okay, so this course, an excerpt from the website, would teach as the antidote to rigor mortis. Rigor mortis is one get frozen when seeing mathematics, right? Math anxiety. The art of educated guessing and opportunistic problem solving. You will work hard. It's not, even though it's the title sounds like that, but it's really serious subject. Okay, so what do I mean by street fighting mathematics? What I mean is the following. Okay. So let me show section 8B and 8C. Okay. You know, section 8A and section 8B tends to be theoretical. And I know that many students, even though you take this course, and I look at the survey, not many students would be really inclined to like math, right? I would say maybe 10%. You know, it's just by experience. So I don't want to really impose the theoretical part to the general student population, even in this course, which is very heavy in math. But I'd like to teach you something that you could use in doing your report, in doing your exam problems. And so that's very practical, right? Anyone would be interested in that. And also very useful in real world application, right? Finite element, for example, the first half of the semester, we did elementary finite element vibration. Not only now that the vibration course is beginning to address, but only even then a particular case of what we did. How many of you are taking vibration now in this semester? I know KZ, who else? Okay, if you take in the future, you're well prepared ahead. Okay. But since there's only KZ, so I don't want to, because there's something very interesting that I wanted to say that I explained to KZ and Michael that I'd like to relate to you. But let me come back to this. So I want to go quickly through the theoretical part, just point out to you what is useful, and then focus on the street fighting, section. Meaning, really, what does it mean, street fighting? It means that you appeal to intuition, okay, understanding in order to get the work done. That's essentially the meaning or the goal of the street fighting mathematics course at MIT. It's not simple, though, like you saw. You will work hard, okay? And anyone interested, you can get into that site and look around and even view a few videos. So that's the plan, So that's what I really want to have, something real practical for everyone to enjoy. I hope, like I do enjoy all of these. And I would strongly advise advanced students or students who really like mathematics to dig deeper into these sections. Okay. So with that in mind, I'd like to go back. Okay. To the top. And so here I have prepared for you, last time I have explained to you with a very concrete example, and there's still some handouts here. I show again, this is the Taylor series expansion of log of 1 plus x. Okay, in very detail, this is a hard copy of my handwritten lecture notes, so there's still 3 copies, so feel free to help yourself. Even though I asked to give priority to those who prefer to have my hard copy lecture notes, but now there are extras, so please help yourself. And I promised to have animations, so I found my animations. And I'd like to show you the animation. I think I can remove these now. Okay, first, expansion of log of 1 plus x about x equal to 0. Okay, let's see. I have my handwritten notes here. Let me quickly remind you that the goal of the expansion was not just expanding into infinite series. Well, this is clearly an infinite series, right? This is the sum of k going from 0 to infinity. But you don't want to write as term 1 plus term 2 plus term 3 and then go on forever. But you want to be able to write in the compact formula like this. And the reason is the following. It's not just that it's elegant, it's beautiful, but it's also very practical. Okay, and the practicality of that is in the animation right here. You see, so this is what I wrote myself. And you see the formula right here. It's very compact, right? It allows me to vary n. You see, so n essentially represents, let me go into projector mode so that the line would be thicker. Okay, so here, you see when n equal to 0, you essentially have the function f log of 1 plus x. By the way, in mathematics, logarithm, when the base is not specified, it's implicitly a natural logarithm. That's ln. Okay. Whereas you probably are used to the log of base 10 and usually denoted by log. So please keep that in mind. In my notes, when I write log, okay, that is implicitly log with the base e, and that's the natural logarithm. Okay, so keep this in mind. And that's why I show two curves here so that you can see the difference between the log of base 10, which is the green curve, versus the natural logarithm. Okay? So what we want to do is the expansion into Taylor series of the natural logarithm. Okay, so I turn off the green line, which is the log of base 10. So now this is n equal to 0, and looks at n equal to 1, right? N equal to 1, you have the straight line, which is the tangent to the logarithm curve at x equal to 0, because we expand about x equal to 0. Okay, so when you have one term, that gives you the tangent, and when you increase the number of terms, you see, now you can see the advantage of writing something that is in compact form, because I can increase the number n to as high as I wish to, and in this code I increase to up to 30, and now let me increase to one more term. You see, so here the blue curve or purple, depends on how your eyes would detect this color. This is two terms, Taylor series expansion. It's also called the truncated Taylor series. And you see it approximates the natural logarithm curve, which is the red curve, right? And locally, meaning only about the point where you do the expansion. Away, you see the divergence, okay? And now let's keep increasing the number of terms, and let me increase to 3 terms. You see, it's the range where the accuracy, where you have accurate approximation, increase a little. But look at the behavior. There's the oscillating behavior in the positive side, and in the negative side, this blue or purple curve does not oscillate about the red curve, but monotonically converge or approach the red curve, showing convergence. So now let me go to the fourth, with 4 terms. You see, in the positive side, it keeps flipping up and down about the red curve. Okay, and then you can do the animation. So you see, in the positive side, it keeps oscillating. In the negative side, there's no oscillation. There's only a gradual approaching monotonically to the red curve. And now, because decreasing, so it goes out and goes in monotonically. There's no oscillation, but in the positive side, there's oscillation. And analytically, you can also explain that, Paul.
I was just going to ask why it only oscillates on the right side.
That's a very good question. That's an excellent question. It takes time to explain. You need to look at the sign and analyze the sign of the terms in the series. Yeah, it takes more work, but that's an excellent question. Let me see. Let me begin to give active learning credits. And I really enjoy questions. And so let's see. This is meeting 34. And Paul, what team number? I keep forgetting. Team 3. Okay, let's see. Yeah. Okay. That's the behavior, and again, the advantage of being able to write something in compact. Otherwise you have infinitely many terms. That's too long, right? Okay. So now, so here is the question. Let me start the animation. Maybe. And move by hand so you can see that even though I increase all the way to 30 terms, and you look at this region here, maybe I can even zoom in. You see, away from this point, which is value 1, the Taylor series never converge, regardless of how many terms you took. Okay, that's the meaning of being local and a local approximation. Now next, if you have something like this, clearly you cannot solve for the solution of the exact function, right, which is natural logarithm, when for any time that is greater than 1. In this region, because the approximation is no longer valid. So that comes to the next question. What if you now, let me bring up the mask so that you're not too overwhelmed, expand about the point x equal to 1 instead of just about the point x equal to 0. And in previous versions of the course, I taught about the radius of convergence, and one can learn deeper about the series. But for this version, I would not emphasize on that, because I'd like to emphasize on something that you would enjoy more. For example, the Beatles and rock and roll, and also very practical application being the use of fast Fourier transform. Okay, but I just want to show to you the animation. Okay, so this is the expansion about the point x equal to 1. Okay, and observe. Let me zoom in so you can observe. It has a similar phenomenon, meaning that okay, so this is when n equal to 1. Okay. Then you have the tangent, and you see that the tangent now is about the point x equal 1 here, right? So we're no longer talking about expanding about x equal to 0. Okay, so the point of interest is x equal to 1. And now observe. If I animate, you see that essentially the domain of convergence is from here, okay, to here. Okay, essentially centered about point 1, right? Because this point is easier to look. This is a little harder to look at. But this point you can see that from 1 to now 3, it would converge, and likewise over here. So essentially, the radius of convergence is 2. Okay, so 1 is the center. So 1 minus 2 is minus 1. So the Taylor series would converge between minus 1 and 3, but beyond, you cannot get convergence. And that's the phenomenon that is called the local approximation, okay, or local convergence. And there's a beautiful theory regarding how you would be able to analytically find the radius of convergence. This is numerical, and this is not analytical, but analytically you can also find the radius of convergence. That's all I want to say about Taylor series. And you may remember, just one last word. Again, this is a series that you can obtain from my lecture notes here, and simply by replacing x hat equal to 1. Okay, then you get the Taylor series about the point x hat equal to 1. And this formula here is general for any point x hat. Okay, and that's how I coded this formula into the animation, and this is what you saw. Okay, so I think that's all I want to say about Taylor series. And let's big picture. Okay, so that's an advantage of filling out the feedback form, is that I'd like to, like I said, my goal is to make your learning experience more productive and more enjoyable. So if I look at something that I need to address, any shortcomings, I'd like to do that. And so one more time, the big picture is before we get into projection on polynomial basis, because these are all related. If you remember section 0B, I think. Yeah. Right here, I have shown this big picture, this is section 0B that pops up since the beginning of the semester, okay? And I pointed out to you already this part, right? This is the local approximation. Now you understand what it means by local. When you move away from the center, the Taylor series no longer converge in general. And then we move to what is called global approximation. And there's a power series that you can construct. There's also Fourier series. And note that Taylor series is a particular case of power series. Okay. And the topic of global approximation here is really very vast and deep in mathematics, and that also includes the finite element method in here. All right. I just don't have time to get deeper into that, and that may not be some of you may not appreciate that, because it tends to be more and more theoretical. Okay, so I'd like to stay concrete, street fighting level. Okay, so now we get into power series, global approximation, projection. I just want to show to you a few, let me go back to this, okay, a few vista points, some main things that you want to keep in mind. So I go back to section 8B, which I showed you last time with vectors, projection of vectors, and this. Yeah, right here. Okay. so let me have two windows so that you have the big picture. And then I will have a window to zoom in. Okay, so you remember I talked about vectors, projecting a given vector on the orthogonal Cartesian coordinate or on the oblique coordinates. Okay, and you may remember that I mentioned that for the oblique coordinates in 2D you can use method that you learn even before statics, but statics would teach you to use a parallelogram, right, to decompose a vector into the sum of two vectors. But you know, or maybe this is a good opportunity for critical thinking question here, and the answer I already gave in the last lecture. What are the disadvantages of that graphical method? Right? Remember, let me pull up my while you are, please think about my question. What are the disadvantages of the graphical method that you learn even before statics? Let's see, it's probably here. Oh, maybe even I remember I did draw that. Mtg.34. Yeah, I could have copied this. Down here. Okay, anyone? What are the disadvantages of decomposing this vector into the sum of two vectors and, you know, in a parallelogram? Colton, anyone else? Remember, I take anyone who raised his or her hands so that more people can get active learning credits. Okay, Colton, go ahead.
It's more difficult to do three-dimensional.
Exactly, very good. 3D, you already get stuck. How do you draw in 3D? This is, you know, the method that you learn in statics or even before statics. This is only applicable for 2D. 3D is already impossible. How about 1 million D? 1 million. That's even, you know, impossible, right? That is just to make the point. But what are other disadvantages? Is that the only disadvantage? Remember, I did mention a very big disadvantage in the last lecture. Colton in team 2. You can discuss with your teammates.
No, it's
Robert?
yeah, what if your vector is a function?
Exactly. You cannot generalize to function. Okay. So, but let me show you a good method to decompose any given vector in a general oblique coordinates that even with 1 million dimensions. Okay. And that is generalizable to functions. And what is that method? And that's in section 8b. Okay. So let me, in a way it's written here. Okay. Let me use a window that I can zoom in so that you can see. Okay, right here. Right here. Okay. Let me just focus on the method. So if you are given, and let me use a mask so you are not overwhelmed with the details. Okay, so if you are given a vector v, right, and let's do in 2D first. Once you understand the method, you can generalize to 3 dimension, 4 dimension, 100, 1,000, 1 million. Okay, doesn't matter. So if you are given a vector v, that means that v can be expressed in terms of the basis vectors of the coordinate of the Cartesian coordinate system. Okay. For Cartesian coordinates, the basis vectors are denoted by boldface E1 and E2. V1 and V2 are the components. Okay. So that's very simple. Now let's give a basis that are no longer orthonormal. Now B1 and B2 are oblique coordinates, and the length of B1 and B2 are not necessarily of unit length. Question: how do you find the components C1 and C2 of the same vector V, but relative to the basis vectors B1 and B2? What's the method beyond the parallelogram? And that method is relying right here on the dot product. Okay, and the dot product now, let's give it a new, let's say, a new face. Okay, so the dot product between two vectors B1 and B2 is now written with the angle bracket. So BI comma BJ. Yeah, so this is BI and BJ, where I and J take values of 1 or 2. But in general, can be take on values between 1 and 1 million and beyond. Okay? So I and J just designate two indices. But here, you know, you want to keep in mind this new notation here. There's a reason to invent this notation. Okay, this is not just to make things more complicated, make your life more complex. No, because this notation here will be generalizable to functions. Okay, whereas this notation here is not convenient for functions. You may misunderstand that this is the product of two functions. Okay, that's not the case. So therefore, the angle bracket is very, very important, and that's the reason. And so from that on, we only use the angle bracket to discuss. And you think of the angle bracket as really the dot product, you know, when we talk about vectors. Whether it's in 2D, 3D, 4D, 100D, or 1 million D, okay, it's a dot product. So what's the method? What's the method to find the components C1 and C2? Well, you know, two unknowns, right? You need two equations. How do you get the two equations? It's very simple. Form a dot product of that equation with B1 and then with B2. So if you take this equation here, right, V, if you reverse, you know, because V is known, right? So you write C1 B1 plus C2 B2 is equal to V with the underbar, meaning a boldface letter designating a vector. So if you take this equation and multiply across, or meaning form the dot product with B1, okay, then you get this one, right? You get C1 B1 dot product with B1, right? Plus C2 B1 dot product with B2, that's the second term, equal to B1 dot product with V. Does it remind you of something that we did before? And where? It's very important. Very, very important. In the first half of the semester, it's a critical thinking question.
Is this like K plus beta M equals 0, or am I totally just off?
K plus beta M equal K minus beta M equal to 0. You are getting closer. Okay, someone build on top of Kevin team 7. Someone wants, you know, Kevin already pointed something really close. Kevin team 7. Oh, sorry, team 7, not team 6. Anyone else? Let me show you the Anderson. So I'd like more people. So Anderson, I'll call you. Let me do this. Anyone else? Let's see. Let's hear. Okay, let's hear Anderson first.
Is
Go
it
ahead.
that the form of that is very similar to the eigenvalue problem?
Similar to the eigenvalue problem. Okay, so that's in a way what Kevin was saying, right? He was saying K minus beta M, something like that, right? So that's the generalized eigenvalue problem. But if you dig a little deeper, let me bring up my lecture notes, and then you can so which one? I think let me try E. me see whether I got it. First try. Okay. Anyone? You see the similarity? You know, and here, when I teach, I'd like to quote, I'll come to you. Montesquieu, okay, who's a philosopher, a French philosopher, and plays an important role in American democracy. He has a quotation that I found quoted in a quantum mechanics book. And his quotation goes as follows: intelligence is defined as the ability to see the similarity between different things and the difference between similar things. Intelligence is the ability to see the similarity between different things and the difference between similar things. What is common between the first half of the semester and the second half of the semester when we talk about solving multiple degrees of freedom system, equation of motion, and now we talk about projection of vectors. What are the similarities? You already saw the difference. The difference is that this is equation of motion, system of second order differential equation, whereas what in my previous slide, that's projection of vectors that you saw, I mean, for 2D using the parallelogram method. You wanted to say
You
something?
kind of lost me. You kind of lost me on over there.
Yeah.
Say like the projection, like the matrix projection.
Matrix projection? Yeah, you're getting close. Yeah, I did use the word projection when I talked in the first half of the semester. But can you point out which equation on this slide here that looks very similar to what I did? You know, with taking the vector b1 and dot product with two sides of the equation. Anyone? Let's see. What is your name first?
Blake,
Blake, and what team number?
3.
Team 3, and I'll come to you, team 3. Okay, Blake. Okay. Yes.
Is it like equation 4 where you're multiplying by phi transpose?
Very good. Excellent. I think Brandon also make the sign for. Okay, so Brandon, and what is your name?
Richard.
Richard, and team 3 also?
Yeah.
Okay, so Richard and Brandon. Don't hesitate. Raise your hand. Get active learning credit. Brandon is team 5. Team 3. Team 3 also. Okay. Very good. Yeah, it's right here. Okay. This is the, remember, the transpose is the dot product. And so what I did here is I take phi bar I transpose dot product across with this equation here, so that I can find the components, you know, at least the first equation. Okay, so see on both sides, and remember let me zoom into these two equations so that you can read better from afar. Right? If you just focus on this part here. Now we have this set of equation of motion. But they are coupled, you know, they are not uncoupled. So in order to uncouple or to find the components, you pre-multiply or do a dot product across with phi bar I. But remember, I goes from 1 to n. So essentially you will have n equations, okay? And then you need to use orthogonality, and that's how you uncouple. But the thought process is the same. That's why this is called projection, right? And now let's go back to the vector case. And I hope that now, looking at both vectors and reminiscing what we did with equation of motion, you now understand deeper the meaning of the word projection, okay? Because this is what you can feel better, whereas the equation of motion, that's more abstract. So let me bring up the mask, and should not forget Anderson. Again, if I forget someone, please feel free to let me know. Yeah, I'll come to you. So Anderson is team 7, right? Okay. Yes, Casey.
So because the angle brackets represent a dot product, the order of what we have in the angle brackets don't matter, right?
Yeah, it's called symmetry. Yeah, we'll have symmetry. Just like a dot product, right? Vector A dot with vector B is equal to vector B dot with vector A. Yeah. And you can explain that because also when you look at the dot product, you take the product of the components, right? And the multiplication of 2 times 3 is the same as 3 times 2. That's how. Yeah, you get symmetric. Very good, Casey. I'll note you down for active learning credit. And while I note Casey down, think about what I did in the next equation there, and that's also opportunity. Let's see. Let me. Yeah. So this is clearly, I hope, is obvious to anyone. I did to get the second equation. Remember, I have 2 unknowns, right? C1 and C2. You need 2 equations to find 2 unknowns. And so this is the second equation. The second equation is obtained simply by taking the dot product of B2 with that equation, expressing the same vector V but in the new coordinates, oblique coordinates, represented by B1 and B2. So here you take B2 and dot with that equation. So here you see C1 is just a scalar, so pull it out. So B2 dot B1 plus C2 B2 dot B2, right, equal to B2 dot V. That's exactly the same thing that we did with the equation of motion. To uncouple that, right? That's, I hope now you appreciate the word projection much deeper. Now you know how to find all of these coefficients, right? B1 dot B1, B1 dot B2, B2 dot B1, B2 dot B2, and B1 dot V, B2 dot V. All of these can be computed because these are just the dot product. You know, the vector V is given, the vector B1 and B2 are given, so therefore all of these dot products can be found. You have 2 equations, 2 unknowns. Period. That's it. That's the method that does not rely on geometry. And this method can be generalized to 3D, 4D, 100D, 1000D, 1 million D. You just have 1 million equations. That's it. But no pictures to draw. One cannot even draw in 3D. I mean, it's harder. You can try. But 4D is really getting impossible. Okay. So that's the method, and you know, this method here is generalizable to functions. Okay, and what does it mean? Projecting a function on a basis. Oh, one more thing before we move on. If you put these 2 equations into matrix form, you get this. Okay, this is the matrix form, where you pull C1 and C2 out, put it in a column matrix, and this matrix here is just formed by the dot product between B1 and B2. And KZ pointed out that B1 dot B2 is the same as B2 dot B1. So therefore this matrix here is symmetric. And it has a name, a very important name called the Gram matrix. Okay? Named after a Scandinavian mathematician, Gram. And the Gram matrix is related to the stiffness matrix in finite element, and the concept is getting deeper and deeper, so I think this is sufficient. But do keep in mind, for those of you who are advanced and like math, you know, so we introduce also a symbol. Gamma is Greek for G, and G is mnemonic for gram, and the arguments of the matrix gamma basically just contain the unit vectors, the basis vectors. Now this notation here is also generalizable to functions. You will have something called the gram matrix of the basis functions, okay? So let me go down to functions now, because solving two equations and two unknowns is really, and I give here an example. Let me zoom out. You know, I give an example in the form of a problem, so feel free to look at the solution guide to find the solution. Okay, but let me go to functions here. So this is very similar to the equation of motion. Okay, so now you're talking about, yeah, thank you, Casey. You talk about functions. Okay, b1 to bn, but in lowercase, and with x in parentheses, that's represent functions. Examples would be polynomials, 1x, x squared, x cubed, x to the power 4. And you want to express a given function in terms of the basis function. You see this, the parallelism and the similarity between functions and vectors. And the notation C sub j is used as mnemonic for components. So you say C sub j are the components of the function f relative to the basis of functions from b1 to bn. And so the question is how to find the coefficient C sub j. And you would use exactly the same method with vectors that I showed you. But what is the scalar? What is the scalar product? Now you can no longer use dot product, right, as a name. And so the scalar product of two functions is in section 7c that I reproduce here, and I just want to show to you on page 37. Okay, so here you see I explained also about the oblique coordinates now. Now I remember that I had that figure. Okay, so here. Okay, so here is the scalar product between two functions is simply the integral of the product of two functions over the interval from A to B, where these two functions are defined. Okay, so keep that in mind. We'll continue from here, and you see the gram matrix and very similar concept. Okay, so lecture summary, please.
Yeah.